Today we're going to take a look at section 3.4, Addition and Subtraction Algorithms. I think we'll get through just the addition ones, but we will see. The whole idea of the word algorithms in this section is a way of doing something, a process by which we do something. Nobody's going to force you to try to adapt or always do your math in one of these ways. Nobody's even going to make you do it, for a long-term kind of project or anything like that. Or maybe even potentially you'll never use some of these methods in your classroom. But if you are in a classroom and there is a resource that's showing your students how to do something in one of these ways, I would hate for that to be the first time you've ever seen them. So I'm going to show you some of the more recent trends in mathematics for how to do addition and subtraction. Sound good? Of course it does. It sounds wonderful, right? Yes, of course. I'm going to go with that. All right, so the first one I imagine that you have seen before. It is called the concrete model. The concrete model is really fantastic. I brought them last time. Remember the base 10 blocks that I brought last time? It's based upon those images. Okay, so if you were physically doing this truly with a child, you would probably be having them actually touch and feel and move the images around, not draw them like we're going to draw them. Sound good? Okay, so keep that in mind. This is just a visual representation on my screen of what your kids would actually be doing physically with manipulatives. All right, so the idea is to draw the images represented by the numbers. So for example, 34 would be 3 longs. And it would be 4 units. Okay, so this is what you would actually have them do. They'd grab the 3 longs, they'd grab the 4 units, and then you would say we need to add 18 to it. So what would that look like whether they grabbed it or whether we draw it? What does 18 look like in a concrete way? 1 long and 8 units. Hang on. That wasn't what I meant to do. Let me try that again. All right, 1 long and 8 units. So this is physically the object sitting now on my desk in front of me as a 6-year-old child, and you're wanting me to sort of put them all together and combine things that can be combined. What do you know as a 19-year-old or thereabouts that you can combine from what we've talked about so far? Okay, so 2 of these and all 8 of these can be combined, right? Imagine like snapping them together like Legos. They can be combined to create a long. Make sense? So I have the original 4 longs that I already had. And then I have 1 more, right? Now I have 5 longs. They're not all sort of evenly in there. And then, what else do I have? 2 units. Not drawn at all well, but the image still has the same kind of pull for us. And if we're counting what we've done, we've sort of drawing an arrow. These 2 things, of course, are equal. If you want to put an equal sign, that's fine. But we've combined them, and now how much do I have here? What does this represent? 52. Okay. Now, this has a wonderful feel to it because what it actually does is it gives a physical representation for this idea of carrying, right? This is what we really do when we carry. We group 10 of these objects together and we carry it into the tens column. So this is a wonderful visual representation for what that shorthand method is that we've used repeatedly throughout the years. Another one then that we're going to look at is the actual standard algorithm. So this is the algorithm that I was just referencing that we've used throughout the year. So you've got 34 and you've got 18. And when you're teaching a standard algorithm or you're thinking about the standard algorithm, where do you start? The left-hand side or the right-hand side? The right-hand side, which can be confusing. And I know you don't feel like it is because you've been doing it for so long, but where do you learn to read? Left to right. And now we're doing math from right to left, and that's not very intuitive. Okay? So all of a sudden now we're doing math from right to left, and we add the 4 and the 8 together and we get 12, and we do this weird thing where we write down a 2 and we carry a 1. It's a little bit weird, okay? But if you're basing that back in this concrete model, you can justify why you're doing that, right? Those ones, those units, there are 12 of them. And 10 of them can be combined and turned into a long. And that's now why it's in the column with the tens, or the longs column if you wanted to be calling it that maybe. And then we have our 1, 3, and 1 making the 5 for 52. Another variation of this method, so this is really just like we've done the same method twice, one in sort of concrete form and one in an abbreviated form, is sort of a mix between. And this is called the expanded algorithm. The expanded algorithm takes the values and actually expands them by the place value that they hold. So instead of writing 34 as 3, 4, we write 34 as 3 times 10 plus 4 times 1. And I'll show you one other version of this too. There's a couple of versions. This is the one I think that your book uses, if I remember right. And then you have the 18, so it's 1 times 10 plus 8 times 1. And then when you add this together, you can kind of actually work from left to right or right to left. So if I go from left to right, which is at least a little bit more intuitive, I have 4 times 10 plus 12 times 1. And then I can break the 12 apart so that I have, I'll move it over a little bit. There's still the 4 times 10. It doesn't change anything. And then the 12 times 1 is actually 1 times 10 plus 2 times 1. And then these two can be combined because they're both times 10s. So it's 5 times 10 plus 2 times 1 for 52. This is not my favorite version of the expanded algorithm. It does work pretty well if you were working with like dollar bills. Imagine you had 10s and 1s in terms of money. It would be a very nice representation for that. You can talk about having 3 10s and 1 10 and 4 1s and 8 1s and grouping the 8 1s or the 10 1s together to turn it into a 10. And you could do it with money really nicely from that way. So it does have a very nice draw in sort of that perspective. The other version of this looks like this. You break the 34 apart as to 30 plus 4 and 10 plus 8 like this. So you're sort of combining a couple of strategies, not really strategies, but visual cues for doing this. You can again work from left to right and talk about this being 40 plus 12 and then breaking the 12 apart by its tens place 2, 40 plus 10 plus 2, so that you have 50 plus 2 or 52. A lot of people, when they're sort of annoyed by the current trends in elementary math, look at our math that we do, these different methods, and say, there's so much writing, it takes so much time, there's so many steps, right? And I understand that, but what you also have to understand is that the goal behind at least some of this early stuff is gaining an understanding of what's going on and then having things that are more efficient. Right? There's two things to be concerned about with mathematics. There's effectiveness, do I really know what's going on, and there's efficiency. And we really don't want to sacrifice one for the other ever. We'd like to have something that's both effective and efficient. And sometimes it's very difficult to sort of bridge that gap and get both those pieces in there. So what we're really seeing happen here is effective in terms of understanding, but not terribly efficient, because there's a lot of writing that we just did. Or over here, there's the drawing that we just did. Or even if we're not drawing and we're actually playing with the tiles, there's having that aspect of it. It's not terribly efficient. There's another couple algorithms we're going to take a look at. This is probably one of my favorites. This is actually the left to right algorithm. Again, it's not terribly efficient, but it's super effective in talking about what's going on. So this is the number 1534 plus 3218. And I'd like to write it visually from top to bottom, at least in part because that's how a lot of the mathematics kids get is already written in. It lines things up nicely. We can see place values lined up. And the idea is to work from left to right. So if we're working from left to right, the first thing we're going to do is we're going to add the 1 and the 3. But as we do it, we are going to recognize that we are adding 1,000 plus 3,000 together. So maybe the kid actually writes 1,000 plus 3,000 down, or maybe they don't. But at some level, your understanding is that this is the number 4,000, because you added 1,000 and 3,000 together. And then you move to the next column, the hundreds column. This is 500 plus 200. And what is 500 plus 200? 700. Okay, then we're going to move to the tens column. This is 30 plus 10, which is 40. And then you have the ones column. Again, we're moving left to right, which is much more natural for us. And 4 plus 8 is 12. At this point, you get to do an additional final step of addition. But the addition has a lot of zeros in it. And zeros are very friendly to add, right? So if you're moving again, the whole goal is to go from left to right. 4 straight down, because there's nothing to add to it, is 4,000. The 7 straight down, nothing to add to it, is 7. We could talk again about the fact that this is 40 and this is 10. But when you're adding straight down, you've got 0 plus 0 plus 4 plus 1, which is 5, very nicely here. There's no carrying involved, right? It's just 5. And then again, adding straight down in the ones column, you get a 2. It's not efficient. There's lots of lines of writing, but it's very clear where all of it came from. And we were able to move from left to right, which is much more useful when you're first learning this. The next one's a fun one, very visual. It's called the Lattice Algorithm. We're going to see the Lattice Algorithm show up again in multiplication too, but it's very friendly. And it starts out looking much like the standard algorithm, 1894, 3218. What we're going to do is we're going to draw underneath it a box. The box needs to be split into 4 columns because we're adding 2 4-digit numbers. Okay? So if you were adding 5-digit numbers, you'd have a box that's 5, columns wide. If you're adding 3-digit numbers, you'd only need 3 digits wide. And then you're going to split the box, and the box is going to be split along the diagonals from the bottom left to the top right. And that's where it gets its name. It looks like a lattice. A lattice is something that people grow the flowers on, right, along the side of a house, like an ivy bush kind of deal. Okay, so that's where this is sort of coming from visually. My numbers don't line up extremely well, unfortunately, so I'm going to move them just a little bit to line them up a little bit better. You can move from left to right or right to left. Doesn't make a lick of difference on this one. So if your goal is to make it more intuitive, which is kind of what we looked at on the last one, we can do that here. If I add 1 plus 3, I get the number 4. And what happens is that the ones digit gets written on the bottom right corner, and if there were a tens digit, it would be written in the top left corner. So like on the next one, 8 plus 2, that's 10. Well, that's a 1 in the top left, is 0 in the bottom right. 9 plus 1 is 10. 1 in the top left, 0 in the bottom right. And then 4 plus 8 is 12. 1 in the top left, 2 in the bottom right. Okay, so we're separating the 2-digit numbers that we get into the tens digit and the ones digit. That's what we're really doing. Okay? And then what you're going to do is you're going to extend those diagonal lines that you created down after the box. Just an extension. Unfortunately, what I'm about to tell you, it does matter that you start on the bottom or on the right-hand side and not the left-hand side, because there could be, at least potentially, carrying going on if we have to add values that are large together. These values are all small, so none of that's going to happen. But we're going to start with the bottom right-hand corner of the box completely on the far right, which is a 2. And we're going to write the 2 down. We're adding it together. So in the next one, what we're going to do is we're basically adding along the diagonals. 1 plus 0 is 1, and it goes in this bottom box right here beside the 2. 1 plus 0 is another 1, and then 1 plus 4 is 5. And my result then is 5112. I would encourage you as you're doing these to make sure you're doing them right. Grab your calculator, check it real quick, or use your standard algorithm, check it real quick, so that you're not accidentally doing something funky and didn't realize it. I mean, you guys have had plenty enough math to be able to double check yourself on these, okay? So I'd encourage you to do that. And if you're not getting it, then you probably have one of the details wrong in how to do the process. And that way you'll know and you can get help to fix that detail that you're missing. Okay? So this is the lattice algorithm. And then the last one is called the scratch algorithm. This is also one of my favorites. The scratch algorithm, and please write yourself a note to the side of this one. This is used best when you've got several numbers to add together. If you were just adding like the last two numbers together, 1894 and 3218, it would not make a lick of sense to use scratch algorithm, like none at all. Okay? The point and the value of the scratch algorithm happens because we're adding several numbers together. A bunch of them, 4 of them, 10 of them, 12 of them, whole bunch of numbers together, and it's very convenient to use. Okay, so we're going to write them again like I was doing on the other ones vertically. So I've got 34, 18, 69, 87. Okay, ready to give this a try? Okay, you do have to work from right to left. Okay, so we're going to start on the right-hand column. And we're going to start at the top of the column, top right. And you're going to add for yourself 4 plus 8. And what is 4 plus 8? 12, right? Okay, anytime you exceed the value of the base that you're in, we're working in base 10 right now. So anytime we get a 2-digit number, we're going to scratch. So we're scratching the 8 out. And instead of remembering 12, we're only going to remember the ones place, which is a 2. Okay, so we're ignoring the tens place. Basically what we're doing is we're scratching to remind ourselves that we are no longer remembering that we just got a 2-digit number with a 10 in it. We're only remembering the units place, which is a 2. So remembering the units place is a 2, we're adding that 2 now to 9. So what's 2 plus 9? 11, and that's a 2-digit number again, right? So we're going to scratch again. We have the number 11. What is the units digit in the number 11? 1. So, whoops. So now we're going to add 1 plus 7, and we get 8, and we write the 8 down. And what we do is we go back and we count the scratches. Because, see, the scratches represented us not remembering that we had a number it was too big. And we did it twice because we had 2 scratches. So those 2 scratches represent the 2 that we did not, the 20, that we did not keep adding together. And we're carrying it now, okay? So now I have 2 plus 3, which is 5, plus 1, which is 6, plus 6, which is 12, and that's too big, so I scratch. And I remember the 2. 2 plus 8 is 10, and so I actually need to scratch again because I got a 2-digit number 10. What's the ones digit of the number 10? 0, and that's the number I write down as the 0. How many scratches did I have? 2, so I will carry a 2 to the hundreds column. I know there's nothing in it, but that 2 will be added to the nothing that we have below for a digit of 2 down here below. So this is 208. Here's the benefit to this. Let me think with you what we would be doing if we were adding this without scratch addition. We would say 4 plus 8 is 12. We can do that no problem because we know our ones-digit additions. There were flashcards for those. You learned them in first grade, and your kids will too, right? They'll learn all of the addition tables for single digits. But all of a sudden then you have a 12 plus 9, and most kids do not have 12 plus 9 memorized. Do they? They don't. And if they do, they might have learned up to the 12s. It's possible. 12 plus 9 they know is 21, but then they get to 21 plus 7, and it may be real easy for you to add 21 and 7 now because of the way you think about math, but for your child, it's probably not. They're going to have to count on their hand or something else, right? Because they don't have the 21 plus 7's, tables memorized. So this eliminates the need for that. It changes everything into single-digit addition, right? Because I can ignore anything that becomes a double digit. I just ignore the tens digit. Ignore it every time, and I scratch it. This is scratch addition. Okay, we do have time to start at least the subtraction algorithms. Maybe we'll have time to do them all. That would actually be kind of nice, and then we can actually talk about the other bases next time. All right, so let's give it a try. We have some subtraction algorithms. First, the concrete model. So we have the same 34 and 18 we had before. We're going to draw 34 out, so you draw it too. 3 longs and 4 units. So this is 34. And from my 34, I want to subtract 18. So subtracting 18 would be removing what? 1 long and 8 units. Very good. I have the 1 long, that's not a problem, but I do not have 8 units to remove. So what do I have to do to actually be able to remove the 8 units? I need to break one of my longs down into units, right? So I take the visual that I have here, and if I were dealing with something that was breakable in terms of Legos, or even if not, you can actually do an exchange, right? You take the long, like from the blocks I brought last time, and change it into the 10 individual units. So we have 2 longs now because we didn't break those apart. We have 10 units that I'm breaking apart. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't judge my inability to draw, please. I know they're not all the same size, but use your imagination. And then I had the original 4 that I had before, right? 1, 2, 3, and 4. So these 2 are equivalent. They're exactly the same amount as what I had before. They're just represented differently. And now I'm physically going to remove from the circle the 18 that I need. I'm going to remove 1 long, and I'm going to remove 8 units. So I think there are 8 right here. And the result from removing these pieces is that I will have how many longs left? 1 long. And how many units left? 6. Wow, that one was so bad I had to redraw it. Okay, that was 6, so I have 16 remaining. We physically can do the changing up. And again, this has a really good application because it's an application or a visual concrete model for borrowing. Right? This is what borrowing really, really does. And that's where we're headed next, is the standard algorithm. So in the standard algorithm, we have 34 minus 18, and we look at the right-hand column and we say something like, I can't take 8 away from 4, so I have to borrow, or change it to, what is the language my son's paper keeps using? Oh, it'll come to me in a little bit. So we put the 2 here, right? And maybe your teacher did something like this where they put the 1 beside the 4 to make it a 14, or maybe they marked it out and put a 14 here. That's okay. That's what it really is, right? We've borrowed 10 and turned it into 10 units plus the 4 units you had originally. And if you're using that kind of language, it makes sense for what you did. If not, it looks really funny because now you've got a 2-digit number in a 1-digit spot. And that's a little weird, okay? But I have physically, right, 14 units now, 14 little bitty blocks. And I have then the ability to remove 8 of them. And 14 minus 8 is 6. I have 2 longs, 2 10s, and I have 2 minus the 1, which would be a 1. So I have 16 left from that perspective. And then we can talk about the expanded algorithm. So far this looks just like what we did with addition, right? Expanded algorithm. We can talk about it in one of 2 ways. We can say that we have the 3 times the 10 plus the 4 times the 1. And I need to subtract 1 times 10 and also subtract 8 times 1, right? Because I got to subtract both pieces. And there's a problem, of course, because if I do this directly, I can't take away 8 from 4. So I have to borrow. The 3 becomes a 2, and the 4 ones become 14 ones, so that when I subtract, I have 1 times 10, and I have 6 times 1 left over for 16. Or you can do it with sort of an abbreviated model. This is 30 plus 4, and then I'm subtracting 10, and I'm subtracting 8. Or if it bothers you to write it that way, you can write it like this. Put a plus at the beginning, or in between them, and put a minus in front of circle, in parentheses, something like that. Again, the whole goal is to break this down. I don't have 3 10s. I have 2 10s. I have 20, and I will exchange that for having 14 here. So either way I do it, I've got 14 then minus the 8. So I've got 6, 10 plus 6, which is 16. Okay, sort of a blend between the standard algorithm and the expanded algorithm in the other form. Okay, we don't have a lattice algorithm or a scratch algorithm for subtraction, but we do have an additional algorithm. It's called equal additions algorithm. Okay, so I want you to write this down. I'm even going to write it because it's so important. The whole goal here is no borrowing. So if at the end of this problem, when you're working this on your own, you ever borrowed, then you made a mistake. The whole point of this algorithm is that you never borrow. So how do we avoid doing that? Well, let me show you. 834 minus 158. So for starters, we start on the right-hand side, just like we have been doing, and we try to say, okay, well, I can't take 8 away from 4. That's a problem, right? So what we're going to do is we're going to add something to the 158 to turn it into a nicer number. And there is no nicer number than 0, because 0 adds and subtracts super well, right? Zeros are wonderful. What would I have to add to an 8 to get it to be a 0 in the ones column? A 2. But you can't go just adding 2 to the middle of a problem without it actually changing. So imagine then if we had to, we've talked about this once before. Imagine that we had myself and my 9-year-old, he's about like this tall now, it's ridiculous, standing up here, and we added 2 inches to his height, like this. Well, he obviously is now closer in height to me, right? So if we add 2 inches, like the 2-inch heel, so that he can ride the ride somewhere because he's too short, we've never done that before, by the way. Don't pretend. Okay, so we add 2 inches to his height. If you want to say that he's still the same distance and height away from me, I also have to add the 2 inches in height to me, right? I have to add a 2-inch heel to me. So now we're actually the same difference in height as we were originally. So if you add 2 to him, you have to add 2 to me. And the same thing's true here. If we add 2 to the 158, we have to add 2 to the 834. So I know we're going to eventually try and subtract this, but our goal is to avoid borrowing. So I'm turning the 158 by adding 2 into what? 160. And sort of just by, not by accident, but by design, by the way I've designed this, when I have to add the 2 to the 834, I will get what? 836. Now, the ones column is good to go, right? 6 minus 0, fantastic, no borrowing. But what happens once you get to the tens column here? I would have to do it again because I can't take 6 away from 3. Now, sometimes when you get to the tens column, you don't need any borrowing and you're done and you just subtract and you're done, okay? But on this one, the tens column still would require borrowing. And if you borrow at this point, then you have totally defeated the whole point of the algorithm, because the whole point of the algorithm is not to borrow ever in the problem. So let's think about the 6, which is the 60, right? It's not really 6, it's 60. What would I have to add to 60 to get the 6 in the tens column to be a 0? 40. So I'm going to add a 40. But if I add a 40 to 160, what do I also have to do? Add a 40 to the 836. So that's what we're going to do. So what happens when I take 836 and I add 40? I get what? 876. And what happens when I add 160 to the 40? You get the 200. And I can now subtract without borrowing. What is 876 minus 200? 676. And that would be my answer. Okay, the whole goal is to avoid borrowing. Okay, this is a good stop spot. Let me just give you a preview of what's going to happen next time. We're going to do the same thing in the other bases. Okay, we're going to have a different series of bases, and we're going to be adding and subtracting in other bases. Again, remember the goal in doing this is to make ourselves feel a little bit uncomfortable, because our kids feel a little bit uncomfortable when they first started in base 10.